Okay. So it's a great pleasure to have here as a speaker of this colloquium Giuseppe Mussardo. The colloquium topic will be exact result in the theory of phase transitions, and the exact result in solvable model of statistical mechanics have been an invaluable relevance in their understanding of the world of phase transitions that are in turn a key element to explain the behavior of the world around us, even outside the strict area of physics. Just for an example, let's think about the DNA. They also have applications in recent experimental physics, such as the search for the elusive Majorana fermion, which was glimpsed in the Onsager solution of the two-dimensional Ising model, or in the physics of the ultra-cold atoms, which were glimpsed in the Bose-Einstein condensation of boson gas. Mussardo is a worldwide recognized expert in this field. It's presently professor at SISSA in Trieste and the founder of its research group in statistical physics. He got there his PhD, then was in Santa Barbara and in Copenhagen, coming back finally to SISSA, of which subsequently was a deputy director. His main research area is non-perturbative statistical field theory, with application both to statistical mechanics and condenser matter physics, with contributions that range, to name a few, from conformal field theory to ultra-cold atoms to exactly solvable model. He was chair of an international important project such as the quantum integrability conformal field theory and topological quantum computations, and Instance, an European network on interdisciplinary statistical and field theory research on low-dimensional quantum systems. Present is also the scientific director of the Journal of Statistical Physics. But Mussardo is a man of multiform talent. He is also a leader in scientific dissemination, internationally awarded also in this field. Always interested in history of science and presently director of history and epistemology of physics at SISSA, he wrote several books on science and for general public, and in particular on the life of Boltzmann, Chandrasekhar, Salam, Pontecorvo, and Galois. And somewhat unusual for a physicist, even related videos of such a quality that the one on Pontecorvo, entitled Maximovich, got the award for Best Scientific Documentary at the International Film Festival in 2014. He's an academician of the Academy of Art and Drawing, and in 2013 he received the award for scientific dissemination of the Italian Society of Physics. So the colloquium, therefore, is an excellent opportunity for the students to be introduced into the fascinating research area of solvable model in statistical mechanics by a guide which is not only expert but passionate. So please.
Thank you. Thank you. Thank you, Alberto, for the nice introduction. Obviously, I'm really honored to be here and to tell you, I hope, a nice story about how nature change its mood and what happens when it does. So the plan of my seminar will consist first of, let's say, a bird's-eye view of the phase transition field. So we'll see several examples we start wondering about, what about. Then I will draw your attention on the fact that there are either statistical or quantum phase transition, and what are the main differences. And behind all this phenomenology, which are pretty rich, pretty, how to say, challenging, there is a beautiful unifying idea, which is the renormalization group. And closely related to it, the fact that we can describe many of these systems under certain conditions in terms of one of the most powerful theory that man has ever developed, which is quantum field theory. And we'll see that renormalization group allows us to understand qualitatively what's going on. In particular, there are what is called a fixed point or a normalization group. I will, of course, define in the due time. And these give rise to a spatial field theory, which is the conformal field theories. And these are incredibly powerful tool to really pin down the dynamics at the critical point. And we'll see that conformal field theory has an ubiquity, namely appear in many other realms of physics. So indeed, there is the embarrassment of the rich, I would say. And finally, I will tell you how also to control, what are the tools to control theories if we just move away slightly from the critical point. And this, in general, will give rise to a theory which involves particle excitations. This particle makes scattering, and natural context, natural language in which one would like to describe them is in terms of the S matrix.
Throughout the ocean,
So,
indeed,
there is an element like H2O, which might have several facets according to the external parameters. So it can be water, liquid, but it can be solid, also with amazing type and structure. But also, if we move parameters, can be vapor, can be things which assume really the form of a gases. Now, this is a really common experience, so common that we not even wonder any longer what's going on in this kind of transformations. Now, in the late in 18-something, there was an Irish chemistry, Andrews, that had the idea to draw a diagram, which is called the phase diagram, in which very easily we can somehow spot the region in which pressure and temperature, for instance, admit matter under the form of gas, liquid, and solid. So in this diagram, there are lines which separate the different phases. There are spatial points, like these three critical points, or these critical points here. And actually, the phenomenology which enter in this diagram is pretty rich because, you see, the critical point is a point in which I can continuously pass, just making this adiabatic transformation, from a liquid phase to a gas phases. So, technically speaking, this point is a point of second-order phase transition. So the terminology comes from the past. So first order, like this one, is when crossing about this, you have a jump in the latent heat. And so you observe really discontinuity in your thermodynamic quantities, while there are other points, of course, you have to think in the region about, that are described by theory where you can smoothly interpolate between two different phases. And these are particularly important for theoretical physicists because while the first order transition, like this one or this one, somehow has a phenomenology which is very much attached to the compound, to the matter you're studying. So for instance, water has a certain feature which other liquid doesn't have. Second order phase transition has, for its own characteristic that I will explain later, the property to be rather universal. So this means that many other substances under broad conditions, which essentially means they live in the same dimensionality as the system you are looking for, and the group of symmetry is the same. For what the critical behavior is concerned, they are absolutely indistinguishable. So from this point of view, second order critical point is what draw the attention of theoretical physicists. Now, phase transition occur, of course, not only in liquid, in water and other things, but occur also in magnetism. So our credit card, we know very well that if we sit on a heating, when we go and try to draw money, gone. So the magnetization has disappeared because the temperature has been higher than the so-called Curie temperature, and therefore the material is no longer magnetized. Now, in magnetic material, you have domain that can be very, very entangled, very, very complicated. And then you might wonder how you measure the spin of a system. Now, this is an experiment done with really a very strong gradient of magnetic field. And the previous liquid found was nitrogen, which doesn't have any spin. So it doesn't stick. But it's enough that you put oxygen, which has a strong dipole magnetic, that you see it sticks completely between the dipole magnets. So people have really wondering phase transition in the magnetism realm. And this is probably the person which is most known in the field, even though he was very humble. This is Ernest Ising. That his only contribution in physics was one paper, essentially, one-dimensional Ising, but this guaranteed him imperator fame all over the world. So he became teacher later on in United States. It's a very interesting story. It's the personal story of Ising. I don't want you to enlarge the story, but he went finally to United States. He was from Germany, and then became a teacher. And everybody knew about him, about what he was doing, because he won a prize as the best teacher in the United States in 1 year. Now, and this is the famous model, the Ising model in 2 dimensions. You know, it consists in degrees of freedom which are up and down, here are black and white, with interaction which is next neighborhood, that when its ferromagnet try to align the spin, so the partner, the closest partner, try to do exactly what the neighborhood is doing. But the actual dynamics is dictated by temperature. So here slowly I'm decreasing the temperature. And you have seen that from completely random and a small domain, decreasing the temperature, the domain of magnetism, either up or down, start to increase very, very large. And as a matter of fact, in infinite volume, you would have really the infinite domain of magnetization. Now, this Ising model is stimulating generation of physicists for decades. You know that Pauli, after the war, wrote to Casimir, say, so what happened during the war? And Casimir said, well, nothing special. There was the atomic bomb, there was everything. Nothing special. But Onsager solved the Ising model. Okay, so it's triggered an enormous amount of interest. And there are many, many questions on the field. In particular, for instance, in more recent time, people have looked at what is called stochastic Loener equation, also to find the fractal dimension of this curve which separates the domain, which is a very beautiful geometrical problem, which can be also interpreted as a phase transition, because you get this fractal dimension only when you are at a critical point. Now, Ising is not the only system. For instance, soon after, Potts, that was a British physicist, invented what is called the Potts model, which easily generalizes Ising, in terms that instead of having only 2 variables, 2 colors, you might have Q colors. And the rule are always that you have a ferromagnet behavior if you give an interaction where colors like to be alike, being next neighborhood, or will be anti-ferro if they try to be completely different color from what is. And by the way, the Potts model in the anti-ferro regime is absolutely close to what is called the 4-color problem in mathematics. That is a famous problem in topology. And the problem is how many colors you need to color a geometrical map in such a way that neighborhood region you can distinguish. And it is believed that the number of colors needed is 4. You might know that the proof has been quite, discussed in the sense that it's the first proof obtained by computer. And in mathematical club, okay, was taken with, let's say, with some skepticism. Anyway, why Potts is related? Because the 4-color Potts means that if you compute the partition function, should have zeros exactly q equal 4. You compute it analytically in the number of color, and then you will find out that should have these zeros 4. Okay, now, phase transition. Now, let's try to be a little more quantitative. Is always a competition between order and disorder. And this is encoded in this expression, which is the free energy of a substances, which is made of a part which is the energy and a part which is the entropy. And the variable can unbalance the two of them is the temperature. So moving the temperature, essentially you are pinned down one in favor of the other and vice versa. Now temperature, an extremely high temperature, you would expect that whatever, degrees of freedom related to the energy should be absolutely irrelevant. And indeed, this is what happens. So if you are on the sun, where the temperature is order 5,000 degrees, there is no structure whatsoever. So you have to decrease enormously the temperature around the temperature of iron when the iron starts to become solid, or our temperature lifetime, to appreciate there are structure in the world. And this becomes more and more evident going down toward the absolute zeros. And this race of absolute zero, as you probably know, was really an obsession for the physicists like Dewar, Omnes. All the second part of the 18th century was, obsessed with this problem, starting from Faraday, who had obtained the first gas liquefying in liquid of chlorine. Now, how to reach this temperature? Well, the first step is like what is called the cascade process. It's how you really hike in mountain if you want to reach the peak of the Mont Blanc. You have to do some camp. First you do the first camp, you reach this, you use this to go another one, you reach another one, and you keep going. So you can use really pressure and the equation of states of van der Waals, essentially, making different quench on this graph to first reach the temperature of the first gas, to use this to liquefy another one. So this is chlorine, this is nitrogen. Then you use this to reach the to liquefy the next one. And so keep going in this way, in this cascade. Physicists of the 18th century, 19th century thought they can reach the absolute zeros. But as a matter of fact, no matter how they try, there was really a very hard problem with the helium. And so this finally was done by Onnes. But nowadays, since we know that temperature is just chaotic motion, so if you want to reach lower temperature, you have to decrease entropy, alias you have to stop the movement of the matter. And this is done essentially with cold atom and laser. Because the laser, what they do is you have some atom in the middle, and you just start kicking them in all possible directions. And so the poor atoms then cannot move in any other direction because receive a kick from the front, a kick from the back, a kick on the left, a kick from the right. So has to stop. And more they stop, more the temperature drop down. And so in this way, it has been reached really astronomically low temperature and has been obtained a famous phenomena predicted by Einstein many, many years before. That is the Bose-Einstein condensation. So this is how nowadays we reach really temperature which are really the order of picokelvin. So absolutely close to the zeros. And then something very interesting happened, because more we go toward zeros, more we are sensitive to the energy scale. And the energy scale is what are ruled by quantum mechanics and by the law of quantum mechanics. And in quantum mechanics, particle is also a wave. And this is a lot of consequences, this correspondence and these equivalence things. So you might have crazy phenomena, right? You might have that things split and go in different directions, and then you cannot explain classically. And one of the phenomena, which is really macroscopically evident from quantum mechanics, is the phase transition of superconductivity, where there are, the theory predict, and this is the result of theory and the phenomenology goes according with it, that a superconductor expels magnetic field, doesn't like to have inside, and this gives rise to what is called Meissner forces, so that if we put a superconductor disk like this in front of magnet, it remains up in the air simply by these magnetic forces, okay? So what happened in this case is that temperature make a change in the ground state of this material and enter in a new phase, the superconducting phases. So this superconducting phase is pretty robust, absolutely robust as far as you are in the range of temperature which allow them. For instance, you are even able to pick up this magnet, as you will see in a minute. So it just, you can move this in all possible way, remain there, and can also make all these kind of things. Now, the equivalent of superconductivity, which is a condensation of charges particle, is superfluidity. Superfluidity, like helium, goes exactly the same mechanism. So when you low down temperature, enter in another phases, which has completely different property from the ordinary liquid that we know, as zero viscosity, for instance. Zero viscosity allowed to have pouring of the liquid out of the wells, as well as it's enough to give an extremely teeny temperature difference that the pressure is enormous, and then eject all the gases, okay? So these are typical quantum phase transition, and is due really to the quantum property of the material. Now, going really to zero temperature, there is indeed phases which are more and more challenging and interesting from a theoretical point of view. For instance, there are what is called topological phases, something which depend by broad property of the system, like braid, for instance. A braid is, two particles are braid or not independently where they are braid, because I can move the braid in the way I want, even though the topology is the same. And this allowed very interesting scheme of quantum computations. Now, this is a subject, this one on entire seminar. I just want to sketch a few things about it. For instance, one of the most robust topological phase of matter is the one related to the quantum Hall effect. When, there is a bar where there is some current going along the longitudinal way, you put a magnetic field in the other one, and then you measure the resistivity in the material, either longitudinal or transversal, and then has incredible stable plateau, which, by the way, is the best measurement of h bar divided e square. And so what is going on here in a broad sense is like you have your electrons which are free at the beginning, but when you put a magnetic field extremely strong, they become really incompressible quantum liquid. So start to have an incredible rigidity. So rigid, then when you pour another one in these things, as a matter of fact, the excitation of the system start to be really, can be splitted in, let's say, in three parts. This is an example, but you can have other fractions. So what I want to say, the excitation in topological system might be fraction of the physical one. And this current, due to carriers of E-third, has been experimentally measured, okay? It's not the electron break, but the quasi-particle with respect to that material has all this fractionalization of degrees of freedom. Now, the quantum Hall effect has this topological property. So this quasi-particle you can bring around, making braids, and these are topological properties, and this can be used to set up a very robust quantum computation scheme, because you know that the main obstacle to quantum computation is decoherence. The fact that you prepare a quantum state, but then poof, just disappear in classical, you have no time to perform the operation you want. But imagine that degrees of freedom are encoded in braids, like this one. Well, braids are much more robust in terms of being more indifferent to the classical world than the others, and you might realize, indeed, the gate of quantum computation in terms of braiding of what is called anyons. Okay? So this is one particular use that you can make of these topological phases. And this will solve at once, of course, all problem of decoherence. Now, this is a bird-eyes view on the phenomenology. So you might have many different realms, this kind of changing mood. Now, you want to have an understanding. Well, amazingly enough, good ideas in physics are few, let's say. But those ones are able to explain a lot. And one of them is this renormalization group idea, due to Kadanoff, due to Wilson, to really great giant of the 20th century physics. The idea is, no matter which system you took, even this room here, there are an intrinsic microscopic scale. It's something given, okay? For a crystal, it might be the difference between the distance between atoms. In a room, it might be a meter. So it's a microscopic scale given. But this is not the only one, because dynamically, the degrees of freedom which made the system start to interact each other and start to talk each other. And there is an influence one to the other, which is captured by what is called correlation length. And all the physics is in the ratio between Xi and A. Okay? Now, the fact is, the renormalization group analysis is particularly fantastic in capture what's going on in the following sense. Are two lines of mathematics, but it's the key point of everything. The key point is, you gave me a lattice, and then I'm going to define what in theory we say an effective Hamiltonian for that degrees of freedom, lattice space A. And how I'm going to define this effective Hamiltonian? The rule of the game is, tell me the group of symmetry of your system. At this point, you know how to write down monomial, which are invariant under the group symmetry. Okay? So if you have Z2 symmetry, all even function will work for you. But even function has a basis of polynomial, which is phi squared, phi 4, phi 6, and so on. If I give you Z3 as a group symmetry, first you should have a complex field, and then you can write down interaction which preserve the symmetry, which is going to be phi 3, because if you make a rotation, come back, rotation of 3, come back in themselves, and so on and so forth. So given any group of symmetry, exists a spatial basis in which you can write down your effective Hamiltonian to that case. You take them all. So in this writing, I'm writing, say, in Z2, all possible even function. Maybe some of the G are 0, but I don't care. I write down the most general expression given the symmetry. Now, if I'm particularly clever, I can choose the basis, then when I make a rescaling of my lattice with B, so I go to larger scale, if I have chosen carefully my variable, this will be called scaling variable, the scaling variable will change simply multiplicatively. Okay? Now, why this is important? Because at this point, formally speaking, the Hamiltonian you get, H prime, has exactly the form as before. The only things that has changed are the coupling constant. So what you have induced is a motion in the coupling constant space. Something like you have your theory define a certain scale, you let it evolve, but then remain always in the multi-dimensional manifold of the couplings. Okay? So you have what in mathematics is called dynamical system. Multivariable dynamical system is what it is. So this, when you make a scale transformation, you are moving in this space. And then you can prove beautiful theorem that the only thing that can happen is that the only place where trajectory can cross are at the critical point. The critical points are defined as that point that no matter how you change the scale, the couplings are always the same. Okay? And you can prove very easily that the correlation length of this critical point has to be infinite. So these are really the critical point of your theories, and I will elaborate more on this concept later. Okay? So formally speaking, it's like you can go like the infinitely large scale of the universe, changing the scale and arriving to scale which are shorter and shorter, infinitely many small, and arrive really keep going. You arrive to a scale where you start seeing elementary particle, you start seeing nucleus, quark, whatever, all the scale down. So I want to say that this idea of scaling transformation is incredibly powerful because allow you to, first of all, to select the relevant degrees of freedom at a given scale. And this is the idea of effective Hamiltonian. But if you really insist, you want to, the ambition is to trace back the theory from the deep infrared, large scale, to the deep ultraviolet. And then the renormalization group will tell you that fixing the group, this trajectory will always be associated to a trajectory of RG. One rule in the infrared, one rule in the ultraviolet. Okay? So the picture geometrically is fantastically simple and net. Of course, to implement, to compute, to identify the critical point is question of a lot of work. So Wilson invent, for instance, the epsilon expansion to start from a theory which you know what it is and try to find out what are the fixed points around. Later, I'm going to show you that in 2 dimensions, I don't need the epsilon expansion. I can identify uniquely all these infinitely many points in one shot. Okay? So this is what is really leading us directly to quantum field theory languages. Because, you can open the book of Weinberg, he said the only way of combining special relativity and quantum mechanics is field theory. So indeed, if we take for granted Einstein relativity, special relativity, and Planck observation of the existence of quantization of energy, we end up indeed in some quantum field theory which has the following properties. So what are in a nutshell the features of field theory? First of all is a theory of particle excitations. Particle which should satisfy the dispersion relation coming from relativity. Indeed, you define what is an elementary particle, the irreducible representation of the Poincare group. So it's a theory of particle excitation. It's local, so taking account the basic property which is locality. This means that all interaction between particles occurs through exchange of particles themselves. And so this gives rise to the famous Feynman diagram, where you want to take in account possible effect of the other particle at a given order in perturbation theory. You have to write down this diagram. It's causal by construction, taking account the importance of the light cone, alias that if you have events which are outside the past and the future light cone, the field should commute. So there should be no interference in this region. Is unitary straight away from the very beginning. Nothing gets lost. So this means that any matrix element that you write, let's say in or outstate particle, you can always rewrite in terms of intermediate basis of outside particle using the S matrix that we discuss later. And finally, has also extra symmetry, which are pretty important. It's called the crossing symmetry. Crossing symmetry is a peculiar symmetry which emerges in quantum field theory, which allow you, given a certain reaction, like proton-proton going in proton-proton, in going the so-called cross-channel, when you are looking the amplitude from a different point of view, and describe equivalently proton-antiproton, going proton-antiproton. So this is called crossing symmetry, and Fermi, for instance, and Young as well, make great use of these properties in the 50s to compute amplitude at that time were quite unknown. And finally, he has inside the bootstrap principle on which I elaborate later on. So one of the consequences of field theory is the existence of antiparticle. This is necessity. The theory necessarily should have antiparticle because it's the only way in which you can ensure causality. So a signal that was there, if only particle was there, is cancelled by antiparticle that, as you know, goes back in time. And this was found out. It's a theory, of course, of scattering. That is what people does in CERN, in try to infer property of matter just using scattering properties. It's also a theory which might have or might not have parity conservation. This is also the great insight of Young, T.D. Lee and Young. And in particular, T.D. Lee is the author of this joke. Namely, do you think he's him or is he him in the mirror? Bet are welcome. Sorry? So you think he's real, he's not drawn in the mirror? Yeah, I can write, of course, like Leonardo on the other way. This is not. Yeah, this is particularly subtle joke because if we do not have a social convention, and if we didn't have the jacket, we can never describe, never discover. So it's a particular way how the male abandoned the jacket. So this is the only way you understand that was him, not him in the mirror. The only way. Otherwise would have been completely impossible. Okay? Okay, now, boiled down, what is the real, to say, distinguished property of quantum mechanics? The fact that we have amplitudes, alias scalar product between some we call vector, so a particle at a certain position at time 0 going and time t, and in quantum mechanics is not given this trajectory by better. The way of going from this point to the other is not just due to the one trajectory, but might occur in many, many, many different ways, as well as we weight this trajectory with the action or the relative trajectory. So from this come out, of course, the principle of minimum action associated to the classical trajectory, but in quantum mechanics we have to take all possible way of performing this transition and weight it according to that. So computing computing path integral generally is pretty tough and pretty difficult. And here is the magic that we learn from Giancarlo Wick. Wick say, well, as far as you imagine or you assume there are no singularity in making this rotation, the Wick rotation, you can compute this path integral going to the imaginary time. So this is the magic of the imaginary path. At this point, the initial quantity become this other one. And why this is important? Because now you have terms which are decreases if the value of the Hamiltonian, it's called when you change this, drop you down the term. And in some sense, you are in business, because the second expression is really probability. You are computing something in the context of probability. So you can compute, say, Monte Carlo. You can have really the most distributed, the most probable distribution value and this and that. You might try to find what are the configurations which make an ensemble of particles the happier possible. This, for instance, is the concept of Bethe ansatz. Bethe ansatz is a particular trick when you have an ensemble of particles subject to interaction. They have certain level that can fill, and the occupation of the levels is done according to a minimum principle of the free energy. Okay? So this is why we are really in business in this way. So coming back to the initial slides I talked about, imagine that you have a statistical model, purely one, Potts model, easing the way you like. When the correlation length is much larger than A, you can do the following trick. So you have to compute the partition function, even of a classical variable. The first trick you do is, being a sum, you can rearrange the term the way you like it. So in particular, you would like to arrange the term adding row by row. And so the sum is going to be something like this. So you are summing one, the other, so on and so forth. And you imagine that you can perform this sum on a row using an operator. So h bar is not the same as h. You compute h bar knowing h, but this is an operator which map the value of your degrees of freedom in one row to the next one. And when you have done all this, you make the trace. And this is the coup de théâtre, because you know, if you take the Feynman-Gibbs book, you find out that functional integral is equivalent to operator. And you have this interchange of languages. So this trace of operator is nothing else than ordinary path integral. And this hold as far as C is much larger than A, and then you get a field theory, and then you are in business. Okay? So I repeat the logic. The logic is, imagine you want to solve easy model in 2D. So you write it down, the partition function, in that particular way. You identify the operators H, this is a linear operator, and then you know it's guaranteed that this expression is completely equivalent to make a path integral on an action which respects the same symmetry of H. And this is how, for instance, in easing, you get 5 to the 4th. Okay? And so this, why is so convenient? Because we know handling with integral is much better than handling with sum. Because in integral, you can make a change of variable, you can make shift, you can do a lot of operation, where in finite sum is pretty difficult in doing that. For instance, if you want to compute easy model with specific boundary condition, in the original formulation is quite hell. But if you have this Hamiltonian, it's just a matrix element of this operator. This is how, for instance, people have classified partition function with many, many different boundary conditions. Because in this formalism, boundary conditions are particular states of the Hilbert space. So you have to classify them according to the property there are no flux of energy passing by them. And their number is finite. Okay? And then you can compute also partition function exactly in this way. So coming back to my picture before, the critical point are theories which has infinite correlation length, which in language of field theory are massless particles. And these are described by conformal field theory, and the region nearby is the so-called scaling region. So I have to tell you what the problem is. the great ambitions of a physicist would be to describe a theory all the way down from ultraviolet to infrared. But you understand that from this point of view, these guys here are really strong coupling. It's when the theory has reached astronomically distance and the evolution of the coupling constant has become gigantic. So this is the so-called strong coupling region, which in general is quite difficult to describe unless you have particular property of your theory which allow you to follow this one. For instance, supersymmetry. This is one case where you are able really to follow this. So what people usually do is that they are happy to describe in full detail what is called the scaling region nearby the fixed point, okay? Which means you sit at a fixed point, for instance, easing at the critical point, and you switch off a little bit the temperature from the critical temperature. The system is no longer conformal, has completely different property, but you are not insisting to go extremely far from it. Or you switch a little magnetic field. So is, technically speaking, where the renormalization group evolution equation is linear. This is called scaling region. But doesn't mean it's trivial. It's highly non-trivial region, but is much more simpler than study completely the flow. So in this, in general, you have massive theories in general. Okay, so the fixed point are this conformal field theory, and in 2 dimensions, there are infinitely many of these fixed points that can be pinned down exactly through the rule of conformal field theory, and each of these fixed points has been identified with precise statistical models. For instance, the lowest one is the Ising model. The next one is the 3 critical Ising model. The next one is the Potts model. The other one is the 3 critical Potts model, and keep going. There are infinitely many of these. How come this? It comes in the following way. So you can ask, what is so special about the fixed point? What is so special is, being the correlation length infinity, at this point you can make all the dilatation transformation you like. The system is completely insensitive to it. Then it might be also rotational invariant, so there are certain properties. And there might be also, so you need only to have dilatation invariant, global, rotational invariance, and translation invariance to guarantee that the fixed point is invariant under local transformations. Local means you can decide to rescale your length differently according to the point. And so you understand this is an incredible, huge constraint. You have a system that should appear exactly the same no matter how it is scaled locally. And you take a lattice, for instance, and you can deform in many, many different ways. The physics has to be exactly the same. So in 2 dimensions, this constraint is particularly powerful because coincide with the infinitely many analytic map of the complex analysis. So you can take this, for instance, the Riemann zeta function, you take it, or you take the Fermat curve, you apply to the lattice, the system has to be completely equivalent, cannot change. So you understand that you should have particular characteristic to be so. And so you take the Riemann sphere, you make what is called the Möbius transformation, which is essentially all the transformation of a football ball. And of course, this has to be, once again, symmetry. But at the same time, you know that any conformal transformation, unless it's a constant, must have singularity. Otherwise, it's a trivial one. So what are the singularity of this transformation? Is where sit the order parameters. Okay? So this means that in this conformal field theory, which has an enormous range of applications, this idea, both in field theory, in Bose-Einstein condensation, in low temperature gases, in exactly solvable model, in classifying braids, in topological phase of matter, in holography, in out of equilibrium physics, is a common language. Many, 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 and these are just a very simple sample of it. And this is due to these simple relations. You have your order fields, then when they are close together, they have power law singularity. And the power law singularity are dictated by their anomalous dimension. Okay? So this is like when you decompose two irreducible representations with respect to a third one, and this constant play the role of Glebs-Gordon. Now, how you solve the theory? You're solving, imposing the consistency of this equation. Alias, you impose that if you have the 4-point function, you can compute either stretching in this way or stretching the other way. And this, immediately you understand, is an infinite number of constraints for the structure constant, which sit here, and for the propagator, because these are the propagator of the particles. So this is called the bootstrap equations, which has to be solved at once. You have no free parameters to deal with. And the solution is a highly non-trivial set. And let me tell you how you reach these solutions. So this is the so-called conformal bootstrap. You reach this solution taking into account the most fundamental field of the theory, which is the stress energy tensor. The stress energy tensor is really the field sensitive to the stretching, to the metric. So this field has an operator product expansion, which involves a constant here. Okay? But for the rest, it's very, very simple. Then you can convert, with a trick of complex analysis, this operator product expansion in an algebraic relation for the modes of this. And so you reach an amazing conceptual conclusions. If you want to classify all critical points, you have to classify all irreducible representation of this algebra. So morally, it's like if you have been subject to a crazy rotation of object, completely complicated, you might do not understand anything. Each one looks completely crazy, one to the other. And then someone comes and say, no, if you want to understand what's going on, you have just to classify SU2. Simple. Because then you have harmonic sphere, dipole, D waves, P waves, are all there. The same is here. If you are able to classify irreducible representation of this algebra associated to the stretching, you have all the critical points you like. Okay? And this algebra depends parametrically on this C and has a feature that you see immediately what they are. There are infinite number of generators, and C identifies the class of universality. Is really a fingerprint of the fixed point, and the anomalous dimension are nothing else than the eigenvalues of this L0, like the eigenvalues of Lz, of Sz in the spin. So this field has the property to be annihilated by all the other. It's like highest weight vector in SU2, exactly the same. The logic is the same. There is here much richer algebraic complexity because the algebra is infinite, but the concept is the same. So for instance, you have the irreducible representation, which are given just applying creation operator, because the commutator of L minus n with L0 is just proportional to this, and the corresponding eigenvector increased by n. So you see at this point you can immediately have all the irreducible representation, keep applying L minus n. And there are also the derivative, of course, in this. notice that this poses a very, very interesting problem of number theory. Because if you want the degeneracy of one of these levels, let's say the level n, this is in how many possible ways you can write the integer n as a sum of lower integers. It's like if you want to go to the 5th floor of a building, you can go, press the lifted 1, 1, 1, 1, 1, or you can do 2, 3, or you can do 2, 2, 1, and so on and so forth. So the degeneracy is associated with the possible path which bring you there with all these oscillators that you have. And by the way, the asymptotic of this is a famous Hardy-Ramanujan formula. So there is an exponential number of states associated to these levels. So among the irreducible representation, there are some special ones when you have a finite number of fields. And these are given. So people have been able to pin down in this huge realm of mathematics models where the central charge is quantized, and for each value of the quantization, you have also the anomalous dimension. Exactly. There is no epsilon expansion, guys. It's exact. And moreover, what is the physical interpretation of this expression? Is very, very simple. So keep P. So it's like if you have a garden where you have trees in discrete position of integers. You draw a straight line whose slope is P plus 1, and the anomalous dimension is nothing else than the distance of this point for the straight line. This is the interpretation, okay? So this gives you another set of rules. The number of relevant operators, the relevant operators are those that if you switch on, move you out from the critical point, are those when delta is less than 1. So you have just to count how many trees there are in this strip. Okay? So given any P, you know immediately the number of relevant operator that the guy is. So for the P model, you have P minus 2 times 2. Okay? Simple like this. So it's really an amazing exact computation. So what is the first of this model? Is the easy model. So if I draw this garden I was talking about, put in the numbers, you get this number. These are the anomalous dimension of the fields. And out of this, you can construct the operator content. So the magnetization of Ising, as well known from Baxter solution, and on Sager and Young, blah, 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 as 116. The energy, there is also duality. Actually, you can prove that this guy is a doublet. Then there is the energy operator. But you can have also the fermions, the Majorana fermion that Pier Alberto was talking before. So the Majorana fermion in Ising is combined two irreducible representation of the Virasoro algebra. Okay? Then you can go to the next one, is the tricritical Ising. So you can repeat and stick in the formula I gave you. You have the exact numbers of the anomalous dimension of the fields, and you have all possible operator content combining these various different representations. And also in this case, you have fermionic fields and all that. And when you compute the structure constant, I'm showing you for an example. You see the structure constant are highly non-trivial function. In this case, are gamma function, a ratio of gamma function. So I want to say the consistency of this bootstrap algebra, you are saying a function with infinite manifold in this channel has to be equal to the function with infinite manifold in the other ones, can only be ensured by very special values of delta, but also very special values of the structure constant. And so, not surprisingly, come up these amazing numbers. Okay. Okay. Now the last part, and then I'm going very quickly to the last one. So I told you broadly how you can solve the fixed point dynamics. It goes without saying that conformal field theory allows me to compute all correlation function I want at a fixed point. Okay? But now imagine that you move slightly away from the point, and you get a theory which has a finite correlation length, a finite mass. So how you address this theory? Well, the theory can be integrable or non-integrable. The difference is when you have an integrable theory, you have particle scattering. No matter how energy you give to this particle, the scattering process are always elastic. So this is the definition of integrable models. On the other hand, non-integrable give you rise to production process. Now this has dramatic mathematical consequences, because on the S matrix, in the first case, when the system is integrable, the S matrix is an analytic function with two very simple branch cut at the thresholds, here and there, and some simple pole in this interval, which are the bound states. While if the system is non-integrable, you have infinitely many thresholds of production, and the analytic structure of the S matrix is as much as hell you can imagine. So you might have resonances, the bound state changes, and so on and so forth. So for obvious reason, I'm concentrated to the integrable one. Noticed that the dispersion relation, the relativistic dispersion relation, can be exactly parameterized in what is called rapidity variables, which geometrically speaking just the area below the asymptote of these things. And in no relativistic limit, this is just the momentum, and this is just a quadratic form. So the S matrix is a relativistic invariant. So if you have two particles of rapidity, beta 1 and beta 2, can only depend on rapidity differences, because it's the only invariant you have. So this is the S channel I was talking about. This is the T channel if you look the process in the other way. This S matrices is a matrices. Must satisfy what is called Yang-Baxter equations. Must satisfy unitarity and crossing, means they should satisfy some particular relation. The sum of all the intermediate states should give you to the identity. Starting from beta and reversing, you should go back to the identity. As well as the crossing symmetry means that you can relate it, the scattering of the process A, C bar, B bar, B to the other one as far as you do an analytic continuation on this. And the pole of these guys give you the bound state. Now, the bound state has to be like this, so a residue time the S, the Mandelstam variable, equal to the pole. So what are the rapidity variables which occur this? So if you substitute in the relation I gave you, is this expression here. You have to read it like this. The mass of the bound state is equal to the mass of the external particle times this term to the cosine of the resonances. Now, this formula we knew from the high school. This formula is the formula of triangle. So this means that the masses entering a scattering amplitude should be side of a triangle. But this has a fantastic consequences, because in a triangle, we know also that the sum of the external angle has to be 2 pi. So this means that if I get this resonance angle in the channel A and B, I know automatically what are the scattering amplitude and the other amplitude. It's amazing. Okay? So everything keep together and is completely consistent. So the bootstrap principle say that all particles are equal, but one which is more equal than the other, which is the lowest mass. So I can start from the lowest and build recursively all the others. Okay? And so this is a recursive equation that if you want to compute the S matrix involving a bound state, you do Yang-Baxter, you just translated this externally, and you compute in terms of product of S matrix involving just external particle. This is an equation, okay? Which from 2 amplitude, you get the third one, knowing the resonance angle. So the rule of the game is very simple. Identify the lowest particle, identify the lowest resonance, all the rest is algebra, okay? So this has been done. What is the simplest S matrix you can think of? -1. Satisfy unitarity and bootstrap. What is it? This is the Ising S matrix description. This is the Majorana fermions, because in the continuum limit, the corresponding theory is a Majorana fermions with the mass, which is just the displacement of the temperature. And so you do this. Now, more non-trivial case is if I take the Ising model and add a magnetic field. Now, in the continuum is an integrable theory, means has an infinite number of conserved charges, but look at the spin of these conserved charges. It's something amazing. It's 1, 7, 11, 13, 17, 19, 23, 29, modulus 30. Everybody recognizes these numbers? These numbers are the Coxeter exponents of E8. These are the power or the Casimir that is conserved in a group, okay? So for instance, 1, you have to just add 1. 1 plus 1 is 2, is the quadratic Casimir. 7 plus 1 is the 8 Casimir. Means exists a polynomial of the generators, which is completely conserved under the group. And 30 is the Coxeter exponents of E8. So amazingly enough, knowing just this symmetry, you might smell that the Ising model has something to do with E8. And this is stunning. The simplest statistical model in nature, black and white, is related to the most complicated Lie algebra group theory, okay? Now, this has indeed consequences. So, this implies that exists a particle which is bound state of itself. Now, what is the resonance angle where the 3 sides are equal? Is equilateral. So the resonance angle is 2 pi over 3. So I know that in the S matrix of this particle, I must have a resonance angle 2 pi over 3. But then that conserved quantity admit a chain of bootstrap, alias 1, 1 might form particle 2, and 2, 2 come back and form particle 1. Now, if you impose the consistency of the bootstrap, this determines immediately what is the resonance associated to this one. And it's 2 pi over 5. And then there are something incredible. Having only these 2 poles, this equation, this bootstrap equation, cannot be satisfied. So you need necessarily a third pole. The reason is, you see, the bootstrap equation is a dance of pole. You take one, you shift it the other way, and you create an amplitude. But since in this case you want that this shift reproduce the same amplitude, with only 2 poles, you cannot do it, because this guy remains the same. So this has to go to something else, and this has to go to something else. So this means the theory should have at least 3 particles. And so you define the masses of this particle, turns out to be exact. And then this is the exact S matrix of the Ising model, exact to all kind of energy. This is the pole of particle 1. This is the pole of particle 2, and this is the pole of particle 3. And then the other you obtain by bootstrap. So what is the final conclusion? The theory is a theory of 8 particles whose masses are absolutely fixed, except the first one, which is how you are measuring magnetic field. But the ratio are completely fixed. The lowest one is the Golden ratio. And then are all these. And then if you are, how to say, enjoy probability, these are nothing else than the probability of a Brownian motion on the Coxeter graph of E8 And of course, the mass which has the lowest probability has to be the farthest node. Then this is the next one, and this is the next one, and so on and so forth. You can complete this graph. So if you make a random walk on this one, you see the asymptotic states, the probability coincides exactly with this one. So in this, make also an association. The lowest particle is associated to this particular irreducible representation of E8. And you can use it to predict the structure of the bound state, which I'm giving here. So this is when you draw the first, the particle which enter in these things, and so on and so forth. You keep going, you complete the entire table. For this, you have to read like this. Scattering of particle 5 with particle 7. What bound state I will find in this amplitude? These are relative poles. Okay? You can complete them all. So, indeed, you can make sense of this E8 structure of Ising. And this was pointed out by Sasha Zamolodchikov. And together with Gesualdo Delfino, we computed all the matrix elements of this theory. Once again, exactly. There are no approximation whatsoever. And people have used material to simulate the Ising model. And the spectroscopy, of course, has to be extremely rich because you have 8 particles with all possible multiple things. So I make the story short. The continuous curve is the curve that I computed. No free parameters. It's not a best fit. And these are the experimental data. Okay? There is no fit. The only parameter I have is how the experimental measure their magnetic field. I adapt my mass, the first, the rest is fixed. So either I was right or I was wrong. Okay, so this is it. And so with that, let me make a big publicity. So all this story, which I make short, of course, for the colloquium, is in full glory report in this book, but obviously it's not the only book which deal with this beautiful subject. There is the Baxter book, which is the oldest and beautiful, the Cardi book, which is fantastic for all the renormalization group ideas. This is a collection of conformal field theory articles. This is the famous yellow book on conformal field theory. Then the Amit on all the idea of field theory, renormalization group, Kadanov, Itzikinson and Druff, the Zinger-Stan, Giorgio Parisi. And also there are books which are oriented to condensed matter problems, like Zvelik, Sachdev, and Jean-Marchi. Let me finish with this. So, quark, lepton, bosons, all these damn particles you cannot see. That's what drove me to drink. But now I see them all.
Okay, thank you very much for this very fascinating introduction to the subject. There are questions?
Sorry if I'm asking a question a little bit on the sidelines of your presentation. You mentioned at some point topological quantum information processing. Would you illustrate to us what are the current experimental challenges to the implementation of topological quantum information processing? Thank you.
Well, I mean, I was mentioning in the relation with braiding, braiding things. Well, I mean, there you must go definitely down in temperature to avoid anion creation because you want them to braid. And you might do all this universal gate, unfortunately not using Majorana, but you have to use what is called Fibonacci anions, which are particular things of quantum Hall effect. Strictly speaking, I do not know the answer on the experimental side. I know that people are severely performed this. There is a big fuss, but I cannot answer. So I don't know.
Questions? Let me ask just one question. There was this special relation between easing and E8. There are some other situations.
Critical easing is associated to E7. And then if you go on, 3 critical pots is associated to E6. And then there are many other relations between groups. Actually, there is a very rule of thumb, which is very, very funny. If you take the central charge of the model and you divide the anomalous dimension that you are using to perturb, you get a number. And let's do this exercise. Easing a central charge 1/2, and the magnetic field is 1/16. You divide 8. You take 1/2 of easing. You divide 1/2, ratio 1, the Majorana fermions. You get critical easing 7/10. You divide by 1/10, you get 7, E7. Okay, I can give explanation. So I want to say there is a lot of marvelous numerology. As far as you know to read these numbers contain an amazing amount of information. So this work also for critical pots, of course. So you might ask, what happened? It cannot be forever. It's true. When it's not forever, you have fractional. These are solitons. And this fraction is the braiding of the solitons. Is the asymptotic expression, the S matrix of the solitons. Yeah.
No questions?
At some point you were saying that if you have a Poincare invariance and a scale invariance, you get essentially conformal invariance, but that's the case only in 2 dimensions, isn't it?
No.
It has been proved? I thought it was an open question in dimension greater than 2.
It's true forever, yeah.
Well, it has been proven.
The difference is that in 2 dimensions, the algebra, the conformal algebra, which strictly speaking is the global transformation, Möbius, enhanced to be infinite dimensional one. In higher dimension, you remain just with the conformal group. So in 4 dimensions, it's 10 generators.
So my memory was that until like 6-7 years ago, people were still trying to prove it, and people were putting papers on the archive and then retracting them. So
no, I mean,
you think it's
on a very general ground, if you have translation invariance, means your stress energy tensor is conserved. If it's massless, the trace is 0. And if it's a rotational invariance, is symmetric. Now, it's enough, these 3 properties of the stress energy tensor, to guarantee that you have a enlarged set of transformations, which are those which satisfy the Killing equation. The Killing are just the conformal ones. The proof is really one line. The point is, in 2 dimensions, this will enlarge to many more, which of course has to be singular. Indeed, is what I pointed out. Is somehow it looks asymmetry, but it's not asymmetry because it contains singularity. The way you control the singularity is the way how you put in constraint on the theory. And at the end, if you do properly, you click the theory and you solve it. In higher dimension, you have to close the bootstrap. So, and this is what people are being busy since some years in doing numerically. So the 4-point duality, they are trying to solve numerically. And they have developed this beautiful program of min-max and this and that, and finding exponents of easing or Yang-Lee or whatever. Yeah.
Okay, I'll ask you later.
Thank you for the nice talk, Giuseppe. I have a question. When you were showing us this, like you were comparing your theoretical curve with
Yeah.
And how did you pick the width of the theoretical curve? I mean, of the peaks.
Yeah.
How did you pick how did you choose the width of the peak? I mean, because
well,
I think
this is Lorentzian, which is really what is
Okay.
being used always.
so it doesn't come from the.
Now, this is a really kind of finite size effect. So you have a broadening because the form factor gives you the height.
Yeah.
And this is absolutely exact. So the ratio between this and that. And then the width, you just use a Lorentzian, that is the one which we used experimentally.
So there's no really any other like parameter from the. Yeah.
No other parameters. No.
Thank you.
Questions? Questions? So let's thank this wonderful talk.